Today's lesson is an introduction to chemical bonding. In this particular lesson, we will start off by defining a bond and what it means to be bonded to another element. To illustrate this concept, we're going to use a concept known as electronegativity, and we'll use Wikipedia just to show you where this comes from. And then we will do a few example problems illustrating how you can determine what type of bond you have. All right, the definition of a chemical bond is a mutual electrical attraction between the nuclei and valence electrons of different atoms that binds these atoms together. Basically, what it's saying is that when there are two atoms that are next to each other, if there's an attraction between some electrons between them, they're going to share a bond. There's three different types of bonds, and the bonds are based on how much one atom prefers the electrons over another. The first type of bond that we have here is an ionic bond. An ionic bond is a transfer of electrons. What that means is that one of the atoms that is involved in the bond really wants electrons, and the other one really doesn't want that electron. So what happens is that one basically passes the electrons to the other. The way we know something is an ionic bond is based off this concept of electronegativity. Electronegativity is actually a term coined by a guy by the name of Linus Pauling in the early part of the 1900s. And what he was talking about was there's a ranking system of the different elements and how much they really would like to have electrons. The scale goes from 0 to 4, and atoms that really want electrons will have a value of 4, and those that really don't would have a value of 0. And it's the difference in electronegativities that determines what type of bonding characteristic you're going to have. So they decided that anything greater than 1.7 or 1.7 or greater would be an ionic type of bond in which there's going to be the taking of the electron from one atom and placing it on the other atom. Now, any values that are a little bit lower than that would be called polar covalent. Polar covalent is an uneven sharing of electrons, meaning that the value is not so great that the one's going to rip the electron from the other, but it is a pretty lopsided difference. So polar covalent, again, is an uneven sharing of electrons, and the electronegativity difference range here would be anywhere ranging from 0.4 up to 1.6. I like to think of this category as how I used to share toys with my brother when I was a child. I was 2 years older, so whenever we got a toy that we were supposed to share, although it was technically both ours and we shared it, I had it most of the time because I was bigger and I could keep it. So the same thing in the world of the atom. There is going to be a sharing, but the one side is going to always have it more than the other. Okay, the final type is called nonpolar covalent, and nonpolar covalent is an even sharing electrons. And that's because the electronegativity difference between the two is 0.3 or less. And because it's that low, neither side really wants it more than the other, so they kind of have this mutual sharing. Now, what I want you to recognize is there is no strict cutoff line here. For example, if you're 0.3, you would be considered to be nonpolar. If you're 0.4, you would be considered to be polar. Now, that doesn't mean your characteristic just instantly changes once you cross that number. It just means that these are the three ranges that we want to go with. So if you have an electronegativity of 0.3, the difference, I mean, of 0.3, it means that one side does technically want to share it a little bit more than the other side, but not enough to consider it an uneven sharing. Now, 0.4 is when it starts to change a little bit, so then we move up to the next category. So 0.3 and 0.4 are going to behave very similarly, but they are going to just change in their technical name or their category. All right, what we're going to do is I'm going to go to Wikipedia right now and just show you how you can find these values and how you will use them. Okay, here I am back at Wikipedia. If you were to type in electronegativity in Wikipedia, it would take you here. What you notice here is I have a table of electronegativities. And in this table, it pretty much shows all kinds of different values. For example, we see fluorine over here is the highest and most electronegative atom, meaning it wants electrons more than anybody else on the periodic table. It has a value of 3.98. Okay, we see some other guys that have pretty high values. Oxygen has a value of 3.44, meaning if there was a bond between O and F would rather have the electrons because it has a higher value. But O would have a greater electronegativity and would rather have electrons more than its neighbor on the left here, nitrogen. And as you see, the trend is that it is decreasing as you go this way. We discussed this in the electronegativity chapter. The guys on this corner are very low. For example, francium only has a 0.7 electronegativity, meaning he has a very low desire to go and get electrons. So depending on what two elements you grab off the periodic table, you're going to be able to tell what their electronegativity is. And by looking at the difference in those values, we can determine our bonding characteristic. All right, so again, use these tables. You can go anywhere on the web to find these, or you can print one out of our textbook or find a table anywhere. It's pretty easy to find one of these things, but the idea here is that we need to have some kind of reference chart to figure out who wants the electrons more, because to try to know them on our own is absolutely insane. Okay, we're going to go to our simulation in a moment, and we will show you how this is done. Okay, here we are back at Inkscape. I've taken some of the values off of that periodic table, showing a couple different atoms and their electronegativity values, and we're going to just use these as our samples. So, for example, let's say I wanted to know what type of bonding type forms between Na and F, okay, sodium and fluorine. If I were to look at these two elements on the electronegativities from the table, I would see that Na has a value of 0.93, very low value, and fluorine has a value of 3.98. So if I take 3.98 and I subtract 0.93 from it, we would see that the electronegativity difference here would be 3.05. Okay, and that is a pretty big difference. In fact, it is so large, it's over our 1.7 that we said, that it is considered an ionic bond. Okay, so what we see here is that all you have to do is check the difference between the two elements' electronegativity, see what it is, and then again, anything 1.7 or higher would be considered ionic, anything 0.3 lower would be nonpolar covalent, and anything in the middle would be considered polar covalent. So we'll take a look at another one. Let's say, for example, I was looking at hydrogen and nitrogen this time. If I looked at hydrogen and nitrogen, again, I go to my table. I see that hydrogen has a value of 2.2, a middle of the road type of electronegativity, while nitrogen next to it has 3.04. So if I were to take the difference of these two, 3.04 minus 2.20, I would see that I get a difference of 0.84. And that value is a moderate difference. It's not quite a sharing number because 0 would be true sharing. So what we see here is that this would be considered a polar covalent, meaning that the value is pretty significant, but not enough where one would take the other one's electrons. So this is a polar covalent type of bond. There's some sharing going on, but it's pretty lopsided in the favor of the nitrogen because he has a higher value. All right, we also can look at a couple others here. For example, let's say we looked at chlorine and oxygen. If we look at chlorine and oxygen, we see chlorine ranks in at 3.16, oxygen ranks in at 3.44. So to take the difference, we take 3.44 minus 3.16, and we see in our calculator, if we needed a calculator, it is a difference of 0.28. Not a very big difference. We see that the oxygen's value is higher than the chlorine, and if we take that value, that means that oxygen is going to prefer the electrons, but it's a pretty even share. So while oxygen will possess the electron a little bit more than chlorine, we'll consider it an overall pretty even share. This would be considered a nonpolar covalent, meaning that the electrons are kind of shared evenly. Neither side has it more than the other. Okay, we'll run one last check here, and let's take a look here. We have magnesium, and I'm going to look at oxygen. So this time, we'll take a look at how magnesium and oxygen look. If we look at their values, magnesium is 1.31, oxygen is 3.44. To take the difference, I'll take the larger and subtract it from the smaller. Okay, 3.44 minus 1.31. And what we would see, that equals a difference of 2.33. That's a pretty huge difference again. Again, we said 1.7 is the cutoff line. If you go over that, it's not very much sharing going on. One really wants it more than the other. That means that this is ionic. Now, what you're going to notice in terms of the bonding is that the two that we had as ionic, if you look, they were consisting of a metal and a nonmetal. Sodium's on the metal side, fluorine's nonmetal. Magnesium is a metal, oxygen is a nonmetal. If you look at those that were covalent, these were both in the both of these were nonmetals, and these were both nonmetals. If you recall in the previous chapter under nomenclature, we started looking at how we did our naming systems, and this is part of the reason why we had to do those naming systems. They behave differently because of these electronegativity differences. All right. Hopefully from this lesson, you recognize now how you can determine whether something is ionic or covalent, and in particular, if it's nonpolar or polar covalent. Please make sure to use my website to copy the notes and take the necessary online quiz. And please be sure to bring any questions with you to class as we discuss this in more detail.